NASA's James Webb Space Telescope, JWST, isn't just finding 5 new exoplanets. It's revolutionizing exoplanet science by characterizing atmospheres, discovering new types, confirming Earth-sized worlds, and revealing exotic planetary compositions, primarily using transit spectroscopy, which involves analyzing light dips, AM spectra, during planet crossings and direct imaging with coronagraphs. It also reveals gases like CO2, methane, and even potential diamond clouds and challenging formation theories. While many planets are characterized, specific discoveries include LHS 475b, an Earth-sized exoplanet, TWA-7b, a Saturn mass exoplanet, and PSR J232222650b, with a weird atmosphere. The James Webb Space Telescope observes stars, looking for tiny periodic dips in brightness as a planet passes in front. It analyzes the starlight filtered through the planet's atmosphere and the different molecules of water, CO2 and methane. It also absorbs specific wavelengths, creating unique chemical fingerprints. The mid-infrared instrument's coronagraph blocks the intense light of the host star, allowing fainter planets to be seen directly. This reveals directly imaged planets, like TWA-7b, often gas giants or brown dwarfs in nearby systems. When a planet passes behind its star, the James Webb Space Telescope measures the drop in light to get the planet's thermal emission spectrum. While many planets are characterized, specific discoveries include LHS 475b, TWA-7b, and PSR J232222650b. The LHS 475b, Webb confirmed this rocky, Earth-sized planet, 41 light-years away, demonstrating its precision for small worlds around red dwarfs. The TWA-7b, a Saturn mass planet directly imaged, much lighter than typical pushing imaging limits. The PSR J232222650b. This is a Jupiter mass object orbiting a pulsar with a bizarre helium-carbon atmosphere, possibly with diamond clouds, challenging formation models. The K2-18b, the James Webb Space Telescope found methane and CO2 in its atmosphere, hints of a water ocean and a potential Hycean world. The WASP-193b. This is a superpuff planet, incredibly low density like cotton candy. Its structure remains a mystery. The James Webb Space Telescope's detailed atmospheric analysis is moving beyond just finding planets to understanding their composition, climate, and potential habitability, revealing an incredible diversity of worlds unlike anything in our solar system. The James Webb Space Telescope, JWST, and the Transiting Exoplanet Survey Satellite, TESS, are two of the most powerful and advanced space telescopes currently in operation. Here's a brief overview of their capabilities. The JWST is designed to be 10 to 100 times more sensitive than its predecessor, the Hubble Space Telescope. It can detect objects that are 10 to 100 times fainter than what Hubble can see. It observes the universe in infrared light with a wavelength range of 0.6 to 28.5 microns. This allows it to study objects that are too cool or distant to be detected by visible light telescopes like Hubble. The JWST has a resolution of 0.07 to 0.12 arcseconds, which is comparable to Hubble's resolution. This means it can resolve objects that are separated by about 1/10 the width of a human hair. Its field of view is relatively small, about 2.2 arcminutes by 2.2 arcminutes. However, its advanced optics and spectrographs allow it to collect detailed spectra of multiple objects within its field of view. It is designed to study the formation of the first stars and galaxies, as well as the formation of planetary systems and the origins of life. It can observe the atmospheres of exoplanets and detect biosignatures, study the formation of stars and planetary systems, and analyze the composition of comets and asteroids. It can observe the most distant galaxies and quasars. The Transiting Exoplanet Survey Satellite, TESS. The TESS satellite is designed to detect exoplanets that are 10 to 100 times smaller than Jupiter. It can detect planets with radii as small as 1 to 2 Earth radii. TESS observes the universe in visible light with a wavelength range of 600 to 1000 nanometers. It has a resolution of about 20-30 arcseconds, which is relatively low compared to JWST or Hubble. However, its wide field of view and sensitive detectors allow it to detect thousands of exoplanets and has a massive field of view, covering about 85% of the sky over its 2-year primary mission. It observes 26 sectors, each covering about 24 degrees by 96 degrees. The Transiting Exoplanet Survey satellite is designed to detect exoplanets using the transit method, where a planet passes in front of its host star, causing a mini eclipse. It can detect thousands of exoplanets, including small rocky worlds, and study the properties of exoplanet atmospheres. It can also identify exoplanets that are suitable for follow-up study by JWST or other telescopes, and monitor the brightness of stars to study stellar variability and asteroseismology. JWST and TESS are designed to study different aspects of the universe. JWST is a more sensitive and high-resolution telescope that can study the formation of galaxies, stars, and planetary systems, while TESS is a wide-field survey telescope that can detect thousands of exoplanets. JWST is more suited for detailed, targeted observations, while TESS is designed for large-scale surveys and discovery. In summary, JWST is a powerful telescope for studying the universe in infrared light, with a focus on the formation of galaxies, stars, and planetary systems. TESS is a powerful telescope for detecting exoplanets and studying their properties, with a focus on the search for life beyond our solar system. The James Webb Space Telescope was launched on December 25, 2021, and has been in space for approximately 4 years. After a month-long journey, it reached its destination, a Lagrange point 1.5 million kilometers from Earth, where it orbits the Sun. The telescope began collecting data in 2022 and has been reshaping our understanding of the early universe since then. Key milestones. The JWST Space Telescope was launched on December 25, 2021, and reached its destination on January 24, 2022. It started collecting data in 2022. The James Webb Space Telescope is designed to last at least 5.5 years, with a goal of 10 years. However, due to the precision of its launch and orbital insertion, NASA estimates that it could potentially last up to 20 years. The limiting factor for its lifespan is the fuel needed to maintain its halo orbit around the Sun-Earth Lagrange point, L2. With the successful launch and course correction burns, the telescope has more fuel available than originally planned, which could extend its operational life significantly. Key factors affecting its lifespan. 1. Fuel consumption. The telescope needs to use propellant to maintain its halo orbit around L2. 2. Station keeping. Periodic thruster burns are required to retain its proper location and orientation in space. 3. Orbital stability. The L2 orbit is unstable, requiring periodic adjustments to maintain its position.